Good morning, everyone. Meeting is going to start soon.
ସେ ଭିଡ଼ିଓରେ କ'ଣ ଏ ଯୋଉ ସାଉଣ୍ଡଟା କହିଲେ ମ୍ୟୁଟ୍ ନା ସେଟା ଆପଣ କହିଲେ କି ଯିଏ ଆସିଲା ବେଳେ ଷ୍ଟାର୍ଟ କରିବେ ଆପଣ କରିଦେବେ ସେ ହଁ ସାର୍ ଆସିଲେ ସାର୍ ଷ୍ଟାର୍ଟ କରିବେ ସାର୍ ସଙ୍ଗେ ସାର୍ ଷ୍ଟାର୍ଟ କରିବା ସାର୍ ଆସିଗଲେ ରବୀନ୍ଦ୍ର ଷ୍ଟାର୍ଟ ଭିଡ଼ିଓ କରିଦେଉଛି ଷ୍ଟାର୍ଟ କରିଦେଉଛି ସାଉଣ୍ଡଟା କି ସଟ୍ଡାଉନ୍ କରିଦେବେ ସେ ଇନାଗୁରେସନ୍ଟା ନହେଲେ ଥାଉ ସେଇଟା ଷ୍ଟପ୍ କରିଦେବ କରେଣ୍ଟ ପଳେଇବ ଯଦି কোনো ଅସୁବିଧା ହେଇଯିବ ସେନେଲେ ସାର୍ କ'ଣ ସେମାନେ ସଟ୍ଡାଉନ୍ କରିଦେବେ ହଁ ଏବେ ଷ୍ଟାର୍ଟ କରିବା ହେଲା ମାନେ ସାର୍ ଡାଇରେକ୍ଟର ସାର୍ ଆସୁନାହାନ୍ତି ରବୀନ୍ଦ୍ର ବେହେରା ସାର୍ ଅନଲାଇନ୍ ଆସିଲେଣି ମଲ୍ଲିକ ସାର୍ ପଟ୍ଟନାୟକ ସାର୍ ରହିବେ ଆଉ ସାର୍ କହିଲେ ଆସିବେନି ହେଲା ହଁ ହଁ ହଁ
agenda କରୁଛନ୍ତି ତ ଠିକ୍ ଠିକ୍
ଦେଖୁଛି ଏ ସେ ଯୋଉ ପେଣ୍ଡ୍ରାଇଭ୍ଟା କ'ଣ
ଆଗ ତମେ ଷ୍ଟାର୍ଟ କରିବ ତ ନା ମୁଁ ମାନେ ସମସ୍ତେ ଆପଣଙ୍କୁ ଫୋନ୍ କଥା ଶୁଣୁଛୁ
Life's battle don't always go to the stronger and faster man, but sooner or later, the man who wins is the man who thinks he can. A very good morning to everyone present here. I am your host, Sonali Raut. Take this privilege to warmly welcome all our delegates on the first day of TPIP sponsored webinar on transport phenomena in industrial processes. TPIP 2020. This webinar is built with the intent of active and interactive learning organized by the Department of Metallurgical and Materials Engineering, ICIT Sarang. Indira Gandhi Institute of Technology, ICIT Sarang, an autonomous institute of Government of Odisha, was established in the year 1982 with 12 departments offering UG and PG courses, including PhD in engineering, science, and architecture. This is the first government engineering college in the state to have accreditation from NBA, AICTE because of its academic excellence. The Department of Metallurgical and Materials Engineering, established in the year 1994, has all the infrastructural facilities along with well-equipped laboratories having state-of-art equipment required for imparting high-quality education to meet the present-day needs of the society. Now I heartily welcome our Honorable Director, Professor Dr. Satyavrata Mahanta Sir, Coordinator TechUp 3, Dr. Rabindra Kumar Behera Sir, Dean Academics Professor Dr. Suresh Chandra Patnaik Sir, our HOD Dr. Prafulla Kumar Maulik Sir, to the webinar on behalf of the Department of Metallurgical and Materials Engineering. A conference or webinar is a celebration of knowledge. All the delegates who have joined this meeting from diverse places across the countries from nook and corners. I hope that all of you will have 5 most productive days, interesting and stimulating discussions. I sincerely wish that this webinar will be a great success, not only as an opportunity to share knowledge and experiences in the field of transport process, observe and study systems, but also as the beginning of long and fruitful cooperation among fellow educators and the delegates. May now I request our HOD, the coordinator of TPIP, Dr. Prafulla Kumar Maulik Sir, to address the audience.
Okay. Very good morning to all of you. So, respected dignitaries on the webinar, Honorable Dean Academy and Examination, Dr. S. Patnaik, respected TechUp 3 coordinator, Dr. R.K. Behera, and dear coordinators of the webinar, dear colleagues, and dear participants, ladies and gentlemen. It is my great privilege to welcome all the dignitaries and participants to the Department of Metallurgical and Material Engineering in the webinar on transport phenomena in industrial processes, TPIP 2020. The main objective of this TPIP is are inherently associated with the majority of industrial processes that involve extraction and refining of metals which are produced by means of a series of unit operations such as the transfer of momentum and kinetic energy, transfer of heat and mass, and the chemical reaction between different operations. In general, such process involve a number of physical and chemical transformations. The rate of these transformations determine by and large the cost of production of such materials. So moreover, the heat and mass and momentum transfer process are an integral part of all metallurgical operations. A good understanding of the principles involved can lead to many useful predictions about implementing uh, um, in plant processing operations and projects, as well as being essential for any process design work. Therefore, our main motto in organizing the webinar is to raise the awareness and promote material technology and engineering as a challenging, exciting, and rewarding career option among faculties, research scholars, and PG and PG students, for which we have arranged the different invited talk will be delivered by the distinct personality from academy and industries. I am sure the experience will be beneficial to our participants. Finally, the team spirit and effort of our faculties that will certainly make the webinar a grand success. Once again, I extend my heartfelt welcome and obligation to all dignitaries in the webinar because in spite of their busy schedule, they are agreed to present with us. Thank you, one and all.
May I now request our Dean, Academics Professor Dr. Suresh Chandra Patnaik sir to address the audience. Sir, please.
Good morning, everyone. Respected Director, Professor Mahanta, TPIP Coordinator, Professor Ravindra Kumar Behra, and then Head of the Department, Professor.
May I now request our Dean, Academics Professor Dr. Suresh Chandra Patnaik sir to address.
Head of the Department, Professor P.K. Malik, the coordinators of this short-term program, both Professor Malik as well as Professor Samrata Behra, and all the faculty members of the department, and all dear participants. And it gives me great pleasure to see that the department is organizing a short-term course on this transport phenomenon in industrial processes. And though the number of short-term courses have been organized, but this transfer phenomenon is very much relevant both to the academics as well as the industrial processes. Uh, Different kinds of, whether it is an extraction plant, process plant, or whether it is a casting and welding processes, or whether it is heat treatment processes. In all this, uh, apart from the thermodynamics and in order to determine the proper kinetics, in order to determine the output, the productivity, and the phenomenon that is taking place, the processes that are taking place, understanding of that will be complete or will be more precise if an understanding of the various transport phenomena taking place in that process, like the heat transfers, mass transfer, and uh, taking place in those processes. So this is very much relevant, and it is necessary for all the students to have an understanding of this transport phenomena. Though metallurgists are good in the thermodynamics and kinetics, but the kinetics will not be can be precisely determined unless we have and apply the transport phenomena in the different processes. Any modification in the process and the various parameters that are in the processes, whether it's the material or whether it is the other parameters, process parameters, all of them they play a role in determining this transport phenomena. And evaluating that and evaluating those through these transfer phenomena mechanisms of the processes, they will lead to a precise determination of the kinetics of the different processes. So this is very much relevant not only to the academic, those who teach, and those who to all the students, but also to all the people who work in industry, professionals who work in industry, whatever be the type of industry, whether it be a process plant or whether it is that is extraction plant, ferrous or non-ferrous, steel, aluminium, or copper, zinc, any of these. Also, it will be relevant to the castings in the manufacturing side, also the welding processes, and also the heat treatment processes. And therefore this course is relevant, and any the updates, the developments taking place in this course should be means dealt with during this short-term course program, and it's necessary to every one of us to update in these new developments taking place and their applications. And there is a also I see that there's a good number of eminent people from academics as well as from industry delivering the lectures, and I think all the participants will be benefited from it, and the course becomes a grand success. So thank you. Thanks.
Thank you, sir. I would like to request the coordinator TPIP 3, Dr. Rabindra Behera sir, to address the audience. Sir, please. Sir, please unmute your mic.
ସାର୍ ସାର୍ ହଁ ଦେଖୁଛୁ ଏବେ।
Good morning, everybody. Respected Director Professor Satyabrata Mansar, respected Dean Academic Professor Suresh Chandra Patnaik sir, Professor PK Malik sir, HOD Metallurgy, Professor Swarnalata Behra, Coordinator of the Faculty Development Program. As all of you and all the faculty members, participants, welcome to the Faculty Development Program. As we know that the material, search in the material for a accurate design for a particular work is still going on. People are searching material. They are not finding a good material for a particular purpose. So advancement in material development is going on very fast. Therefore, it is necessary to update ourselves with the latest material, latest technologies, and we have to train our students accordingly. This is an attempt to educate all the faculty members with the latest methodology, latest technology in the direction of material development. I hope that with the TPIP funding, we are organizing such programs to update our faculties and faculties and around our institute in the latest development of technologies. I hope this program will be very much helpful for you to update yourself and deliver the new technologies to our students so that they will also be benefited. And thank you very much.
Thank you, sir, for your valuable words. May now I request the coordinator of this webinar, Mrs. Sonlata Behera ma'am, to extend the vote of thanks. Ma'am, please.
Good morning to one all present here, estimated dignitaries of this event, respected Director Sir, IJD Sarang, Dr. Satyabrata Mahanta Sir, respected Coordinator TQ3, IJT Sarang, Dr. Rabindra Kumar Behra Sir, respected Dean Academic and Professor Department of Metallurgical and Materials Engineering, IJT Sarang, Dr. Suresh Chandra Patnaik Sir, respected Head of the Department and Metallurgical and Materials Engineering, IJT Sarang, Coordinator of the program, Dr. Prafulla Kumar Malik Sir, dear participants. On behalf of me and the organizing committee of the TechCube 3 sponsored webinar on transport phenomena in industrial processes, I welcome to all the inaugural ceremony of the program. I am glad to inform that a good number of faculty members and research scholars from reputed institutions and also engineers from various industries have shown interest to participate in the course, and we can expect a healthy interaction among the participants and the estimated research portions of the course from reputed academic units, PSUs, and research organizations. I am very much thankful to our director, Ajay Saran, for his kind approval to organize this event. I am also thankful to the TechCube 3 coordinator for providing financial support for the program. I extend my heartfelt thanks to HOD, our department, and coordinator of the program for his support. I am also thankful to the Dean Academic for his continuous guidance and support. As a coordinator, I am very much thankful to our departmental faculties and staff for their support, the host for the event to coordinate the online event, the Zoom online cloud meeting for providing us this platform to organize this webinar. At last but not the least, I am very much thankful to the participants for showing interest to be the part of the program. Thank you all.
Thank you, ma'am. Now we will resume after 15 minutes of break. Welcome back, everyone. Now the time has come for our esteemed guest, Dr. Manoj Kumar Moharana sir, to deliver his talk. Dr. Manoj Kumar Moharana is currently working as Assistant Professor in the Department of Mechanical Engineering at NIT Rourkela. He had his BTech from College of Engineering and Technology, Bhubaneswar, MTech from IIT Kharagpur and PhD from IIT Kanpur. He got Sastry Scholar Travel Subsidy Grant Award 2010-11 to visit University of Alberta, Edmonton, Canada, and DAAD Fellowship to carry out research at IKE University of Stuttgart, Germany, and also got J.B. Benu Memorial Award in the year 1992. He had many research publications in national and international journals and also attended many national and international conferences, seminars, and workshops. He has conducted short-term courses and workshops. He has membership in many professional bodies. He has 16 years of teaching experience and around 35 MTech and PhD students are taking guidance under him. So, I request Dr. Manoj Kumar Moharana sir to deliver his valuable talk. Please, sir.
Thank you, all the participants, and I thank the organizers especially for giving this opportunity to talk. So today I will be talking on microscale fluid flow and heat transfer. Are you getting my screen now? So please respond. Are you getting my voice?
Yes, sir. Your
Yes,
voice
sir,
is
yes,
audible.
sir. Audible, sir.
Are you able to get my screen?
Yes, sir. Yes, sir.
You are able to see it?
Yes, sir.
Okay. So should I proceed then?
Sir, which screen? Sir,
Computer screen.
not, sir. This is not visible.
Computer screen is not visible. Okay, let me
Yes,
check
sir.
it. Are you able to see it now?
No, sir.
No, sir. No, sir.
Are you able to see it now?
Yes, sir. Yes, sir.
My PowerPoint is visible. Huh? So now my PowerPoint is visible.
Yes, sir.
Okay. So thank you once again. So considering that the title of this program is Transport Phenomena in Industrial Processes, I will try my best to talk in line with this program, and I will try my best to explain you in the simplest form. Whenever you feel any doubt, you can stop me and you can feel free to ask your doubts. So I have titled this talk to be Numerical Prediction of Microscale Fluid Flow and Heat Transfer. The objective of this talk is to predict heat transfer and fluid flow in microscale devices, especially your micro heat exchanger using the knowledge of computational fluid dynamics. It is expected that at the end of this talk, the listeners will be able to understand what is axial wall conduction and important phenomena in heat exchangers, and understand capability of computational fluid dynamics predicting microscale fluid flow and heat transfer. When you think for transport phenomena in industrial processes, you will see from the chemical engineering perspective, three important aspects for transport phenomena are momentum transport, heat transport, and mass transport. So these three are very important from chemical engineering perspective as well as from mechanical engineering perspective also. These three areas, so normally being described through differential equations, what we call as governing differential equation. So these are nothing but slightly complicated mathematical equations, especially partial differential equations that describe different engineering phenomena. For example, flow of water in a heated pipe, a very commonly used application in many situations. For example, now it is a time for cold weather, and morning when we are preparing ourselves for going to our office, so we need little bit of hot water, so we switch on the geyser so that after maybe 2 to 5 minutes we can get hot water in our tap. This is a typical photograph I have taken from Google. We can say especially a process plant. If you closely observe, everywhere what you see is nothing but only pipelines and few heat exchangers. So these industrial processes will mostly involve your pipelines and heat exchangers. And here you find out the left one is the actual photograph of one typical heat exchanger showing the internal sectional views. The right hand side one is a heat exchanger photograph created through some means of three-dimensional CAD softwares. Again, here I have two more heat exchangers. Here you can see in this one the heat exchanger from Kelvin showing the details of pipelines through which this fluid is flowing. Along with, you see these are the pipelines, fluid is flowing, and you have this fins attached to this one. Basically, the objective of fin we know is to increase the surface area. Through this means we are able to increase the overall heat transfer. So again, this is a one kind of radiator heat exchanger. You see cell and fin heat exchanger. Then here you see this is a brass plate heat exchanger. So plates have been modified into different forms, stacked together to form a path for the hot fluid and the cold fluid. You see this red arrows indicating the path for the hot fluid and this blue arrow indicating path for the cold fluid. So interact between them occurs through a partition solid wall. So there will be heat transfer from the hot fluid to the solid fluid interface of the this plate. Then inside this solid plate there will be conduction and heat reaches to the other surface. That means the cold side of the solid fluid interface. Again there will be convection to the fluid. That means here will be convection from hot fluid to the plate, conduction through the plate, again convection from the plate to the cold fluid. So if you think for a conventional heat exchanger, what are the sizes? So sizes may vary from a small one. Small one means we basically say maybe something of the size of a desktop computer or little bit bigger. And it can go as big as you can see here in this diagram. For actual photograph, you need to visualize. You see here, two persons are there. They're basically working welding, doing the welding work on the heat exchanger, and from there you can you should be able to just guess what is the size of the heat exchanger. Here you can see this is probably the diameter of the system, and this is the length of the system. And the typical human being is here. So human being height will be approximately in the range of 1.5 meter. Let's say if you take. So this one we can say minimum 3 to 4 meter diameter, and this length will also probably maybe 4 to 6 meter. So from here you should get the idea how the big process plant heat exchanger can be. This second photograph also will give you some more ideas. You see here, this is the height of this technician, and here you can see this is the partial shown the overall height of the heat exchanger system. That means we can say conventional heat exchangers are normally bigger in size. However, now the world is approaching towards miniaturization. So what is miniaturization? It is nothing but reducing the size of the overall engineering system proportionately. That means, for example, if you want to reduce the size of this one here, so we need to reduce the size proportionately. That means, let's say if you are going to reduce the diameter by 80%, then the length also needs to be reduced by 80%. So that if it is a 4 meter diameter, if we convert into let's say 0.5 meter, that means we made it to 1/8. Then here again a 6 meter diameter will be 6 by 8. Accordingly, you should take this overall length. So this is called the miniaturization. And this photograph will give you the idea how small a miniaturized engineering device can be. So here you can see this is the device with the passage here for fluid flow, and you can just imagine what should be the order of the hydraulic diameter by just taking the size of the nail of a person holding this small device. So it will be hardly this length may be maximum 1 centimeter in length, and from here you should get the idea how this will be. This will be hardly 1 millimeter or less than 1 millimeter. This will be. So hydraulic diameter maybe of the order of 1 millimeter or even less than 1 millimeter. Then here you get the second photograph. This is just very small heat exchanger. To get the idea of how small the heat exchanger is, here they placed a coin here. So normally the coins will range in the something diameter will be maybe 5 mm to hardly 10 to 12 mm only. So that means the heat exchanger size is even smaller than that of a coin. Again here you see this is a scale here. From there you get the idea. So how much is this length? This is hardly around 2.5 millimeter only. Then here you can see this is a heat exchanger. One may be your hot fluid passage, second one will be cold fluid passage. So inside there will be interaction for heat transfer from hot fluid side to cold fluid side. And the presence of this scale gives an idea how small a heat exchanger will be. Even here you can see a little bit bigger to the very small heat exchangers are given here in this photograph. Then this is a microfluidic device. You need to guess the cross-sectional hydraulic diameter of this channels. You are able to see here as a thread or pen lines only by looking at the needle that they have kept it here. So from there you should get the idea that they are very small in nature. This is another photograph of a microfluidic device. So now question arises, why there is a need of so small fluid flow and heat transport devices for various applications. If we consider the flow passages, the fluid flow inside this channel or tube or duct, whatever we say, is integral part of many natural systems as well as many man-made systems. So basically, the human being got the idea for creation of flow passage devices by observing the natural flow passage devices only. For example, this natural flow passage devices include like your biological systems consists of your brain, lungs, kidney, intestine, blood vessels, etc. For example, just to imagine how fluid blood is flowing in your body. It is another fluid just like your water. Or so you can see what would be the approximate hydraulic diameter of the passage through his blood is continuously flowing 24/7 inside your body. Then when you think for man-made systems dealing with flow passages include heat exchangers, maybe nuclear reactors, maybe desalination units like air separation units. These are listed few, so the list can be infinite in length. And how the fluid passes occurs? The fluid passes or the transport occurs across the channel wall, and the bulk fluid takes place through the cross-sectional area of the channel. So basically the cross-sectional area will decide how much fluid flow can take place through a flow passage system. And this channel cross-section, that's why plays an important role for transport of fluid from point to point with the help of the closed walls. A channel or a flow passage, it accomplishes two objectives. First objective is to bring the fluid in contact with the channel wall, and it takes the fresh the fluid, remove the old fluid and brings the fresh fluid continuously. And we need a pressure difference for fluid to flow. Normally engineering applications, we create pressure difference by using a typical engineering device called the pump, which basically operates on electrical power, and it creates pressure difference which causes the flow of the fluid in the desired direction as per our requirement. So the rate of transport process basically depends on the surface area. So this is very important on the surface area, and the surface area depends on the diameter of the circular tube. So if you consider a circular tube, the surface area depends on the diameter. So we can do simple mathematical calculation. This will be, for example, if you consider a let's say circular tube, let's say D is the diameter, then and length is the L is the length, then the surface area we will get 2 pi into R into L. So 2R is equal to D. So that will be pi into D into L. So this is your surface area. So you can see here surface area depends on the diameter here. If you consider the length of the system is constant, if diameter of this pipe or duct increases, then surface area increases. If diameter decreases, then surface area decreases. But this flow rate, it depends on again cross-sectional area, which will linearly vary with d to the power 2 here. So this is a superscript here, d to the power 2. That means if diameter is increased by 2 times, then flow rate will increase by 4 times because it is a d to the power 2 here. But this tube surface area to volume ratio, that means we will calculate the surface area per unit volume. So then this will be proportional to 1 by D here, because you see here area proportional to D, area proportional to D square, volume proportional to D cube. So area to the volume ratio will be proportional to 1 by D. That means if D will increase, then surface area to volume ratio will decrease, and if D will decrease, then surface area to volume ratio will increase. That means we can increase a surface area to volume ratio by decreasing the diameter of a passage. So you can say as the diameter decreases, the surface area to volume ratio increases, and the more the surface area to volume ratio, the more will be the transport process rate, the higher will be the rate of transport process, be it heat transport or something else. So this photograph will give you idea about the order of different engineering devices in different range of scales. For example, the conventional sizes in the range of 25 millimeter comes your boiler, comes your condensers in power plants, and little bit smaller around 2.5 millimeter are compact heat exchangers, and refrigeration evaporator and condensers, which are basically heat exchanger devices, and still smaller in the range of 250 micrometer are electronics cooling. So nowadays we are very much habituated with using electronic devices. The simple one is your smartphones that always remain in our pocket. From our experience, we know that when we continuously use a smartphone or maybe a laptop or a digital pad, it gets heated after some time. This is because continuously heat is being generated inside the system. So we need to remove this heat periodically. So that is called electronics cooling. So cooling of electronic devices. So the orders remain in the range of 250 micrometer. Then still smaller applications are also there, like your capillary actions. So we say it is a duct or a channel, both are same. The function is to help for movement of the fluid from one point to another point. So now we call when the diameter, when we consider it is a circular tube, then we consider D is the diameter. And for non-circular tube, so very frequently used is your rectangular channel or rectangular tube or rectangular duct. And one special case of rectangular is a square tube or square duct. And any other shapes also possible. Maybe here elliptical shape, or maybe we can say star shaped, whatever maybe. Then these cases we represent called DH, D square H, that is called hydraulic diameter. This is defined as 4 into area of cross section divided by weighted perimeter. So when this hydraulic diameter is greater than 3 millimeter, then we call this to be a conventional channel. And when the hydraulic diameter is reduced, which lies in the range of 3 millimeter to 200 micrometer, then we call this to be a mini channel. And if we further reduce the diameter below 200 micrometer but above 10 micrometer, then we call them to be a micro channel. And still further down you go, then we call the transitional micro channel. Then still down we call this to be nano channels when the diameter is still very small. We know that this is a simple mathematical expression for calculating the heat transfer coefficient H, because we define a dimensionless heat transfer coefficient Nusselt number, that is equals to HDH by Kf. Kf is the thermal conductivity of the fluid. In case of a small channel, so let it be mini channel or micro channel, the hydraulic diameter is very small. So that's why since hydraulic diameter is very small, so flow rate will also be very small. Accordingly, the flow will be mostly laminar in nature, for which we are using something called your Reynolds number, RE. So Reynolds number is mathematically defined as rho u dh by mu. So if diameter is less, that means Reynolds number will be less. So when Reynolds number is less, flow will be laminar in nature only. So when flow is in laminar, we know that the axial variation of this Nusselt number for laminar flow for a fluid subjected to, let's say, constant wall heat flux or constant wall temperature. In the developing region, gradually the Nusselt number will decrease, and in the fully developed region, the Nusselt number remains constant. So along the length of the fluid. So this value is equal to 4.36 when you apply constant wall heat flux boundary condition, and 3.66 when you apply constant wall temperature boundary condition. And this developing length will be very small in case of mini macro channel, because this developing length represented as X hydrodynamic, that is equals to 0.05 RE/dH. So Reynolds number is small, hydraulic diameter is also small. That's why this developing length will also be very small. Let's say total length is 60 millimeter for a channel. Out of 60 millimeter, the developing length may be hardly 2 millimeter or 3 millimeter, something like this. So that's why, considering that the developing length is very small, we can assume that flow is almost fully developed throughout the channel. In that case, the average Nusselt number will be almost equal to this local Nusselt number only. So we consider Nusselt number to be constant. K is the thermal conductivity of the fluid, which is constant. Therefore, from this relation, you see H is inversely proportional to the hydraulic diameter. So from here we get, the smaller the hydraulic diameter, the higher will be the convective transfer coefficient. Higher the convective transfer coefficient, higher will be heat transfer by convection. So heat transfer convection relation is HA delta T. So Ts minus T infinity. So once you get smaller channel dimension or hydraulic diameter, we get higher heat transfer coefficient. Higher heat transfer coefficient, we get higher heat removal capacity. That's why micro channels are capable of removing high heat flux. So there is a basic difference between total heat transfer and heat flux. So the flux is the total heat transfer divided by the area. So per unit area, the value may be very high. So total magnitude may be very small. Let's say our mobile is generating only maybe 0.5 watt of heat. But since the processor of your mobile is hardly 1 centimeter by 1 centimeter, so in 1 centimeter by 1 centimeter area, let's say 0.5 watt is generated, then you can calculate how much is the flux. It is 0.5 watt per cm square. So that means 1 cm square will be 10 to the power minus 4 meter square. So you will get 5000 watt per meter square. So that means in 1 meter square area, 5000 watt of heat is being generated. So magnitude wise it is very small, however intensity wise it is very high, and this can damage your electronic devices. So the heat needs to be removed continuously from this place through this microchannel based cooling solution devices, so that we can maintain the temperature of our electronic device below the safe operating temperature. However, considering that surface area is more per unit volume, the pressure drop will also be very high. So you can see here in this plot, you see by decreasing the hydraulic diameter in this direction, we are able to see how the heat transfer coefficient is increasing for water and air, along with how the pressure drop is also increasing here. So that means using mini micro channels, heat transfer increases, also the pressure drop increases. So increase in pressure drop is not good. However, increase in heat transfer is good. So we need to compromise between heat transfer and pressure drop. So increase in pressure drop, we call them to be pressure drop penalty. That means we need to overcome this pressure drop by giving using extra power to run a pump that can sustain this pressure drop and cause the fluid to flow through this microchannel based devices. So here I have listed these advantages of small flow passage devices like mini microchannel. Heat transfer gets enhanced. It can remove high heat flux, especially your electronic devices, and it can meet the demand for cooling microscale devices like your laptops, your high-speed computers, servers, etc. Then from chemical engineering perspective, if we consider a reactor, chemical reactor. So if the chemical reactor is bigger in size, we may be requiring a lot of catalysis. However, if it is smaller in size, the amount of catalysis required is small. Secondly, if let's say some explosion occurs because of something, then if it is a bigger size reactor, then the damage will be very high. Whereas for a small reactor, the damage will not be so high. So this is also the advantages. Secondly, the efficacy of this catalysis for micro scale reactors will be very high compared to a conventional chemical reactors. So this slide gives an idea of different microfabrication techniques developed with time and their order of accuracy. You can see here. Here this scale indicates different order of dimensions. For example, ultra precision milling can do the work in the range of 100 to 1000 micrometer, whereas this laser ablation can go up to, let's say, 6 to 8 micrometer. And E-beam lithography can go up to 0.1 micrometer. So very small components can be fabricated because of developments in microfabrication technology with respect to time. So this photograph shows the actual test section of a mini microchannel based heat exchanger. Here we are not able to visualize anything, but simply you can say, you see here there is a small steel tube. If you see this one, the cross section diameter is hardly 1 millimeter. That means fluid will enter here and fluid will pass here in this direction and fluid comes out here. Here you can see a viewing window for visualizing the flow in this one here. And if you closely see, this is the actual photograph of the micro channel that is fabricated on a steel substrate. So it looks to be very bigger. This dimension is hardly in the range of 2 to 3 millimeter only. So from there you can guess what will be the size of this channel. Here you can see here, this is the inlet and this is the outlet. So that means the channel is placed here, that is called the micro channel. And if you see this micro channel under microscope, you will be able to see this way. You can see this is the channel for the fluid flow here, and this is your thermocouple slot. That means a micro slot have been created to measure the temperature of the wall. So you can see here, this is the very small gap. That means we are trying to measure the temperature of the solid as close as to the solid fluid interface possible. You see here, this is the solid fluid interface. This is your fluid medium. This is the solid medium. See, similarly, this side, this is the solid fluid interface. This is the solid medium and this is the fluid medium. And again, if you cut this macro channel here, that means here, and you see the under microscope, then this is how a micro channel will look like. It can be a rectangular shape or any other shape depending on what are the different fabrication technology we are using. Again, the same photograph here. And when we are interested to study fluid flow through microchannels, then we need to have a experimental test rig to be developed. So basically, for flow to take place, you can see here this photograph you may be finding to be very complicated, but let me explain you here. This is the fluid flow path cycle. You can see this one is the test section. So what is the test section? You can see here whatever you have seen here in this photograph. So this is the test section. So that means, and inside the test section, what is there? Inside the test section, you have this micro channel. Fluid will enter here, flow along this channel, and leave the test section here. And here you can see in this diagram, fluid enters through one pipeline, flows through this channel here, and leaves through the other pipeline here. Then this is a condenser. So you see here, cold fluid enters into the test section. It is being heated to simulate heat generated in electronic devices. Then at the outlet you get a hot fluid. In situations you can get it a phase change also from liquid to vapor. And if it is a phase change liquid to vapor, we need to cool it to bring back from vapor to liquid. If it is a hot fluid at the outlet, we need to cool it to the previous temperature, for which we are using a condenser. And the condenser is connected to a constant temperature bath. The constant temperature bath helps to maintain the constant temperature in the condenser. So now again we get the fluid here, and this fluid we store in a coolant reservoir. We can say this is a simple tank, and from the coolant reservoir or a tank, we need to feed the fluid continuously to the test section with the help of a micropump, because the channel dimension is very small, maybe 0.2 mm, 0.3 mm hydraulic diameter. So flow rate will be very small, maybe of the order of 2 ml per minute, 3 ml more per minute, even less than these values also. So we need a micropump which can maintain a flow rate in this order. So now here in a microchannel based heat exchangers, whatever you see here, for example, this one, whatever you see, this one, microchannel based heat exchanger. And this is the assembly view of this microchannel based heat exchanger. Very important, crucial something is called axial back conduction, which influence the overall performance of the microscale heat exchanger. So let us understand what is axial back conduction here. So to understand axial back conduction, let us visit to the textbook on heat transfer for flow through a circular tube. Let's say you consider a circular tube, and we will apply heat on the outer surface of the circular tube. So what are the two standard boundary conditions available? One standard boundary condition is applying constant wall heat flux. That means we will give equal amount of heat at every point throughout the outer surface of this tube. That is called constant wall heat flux boundary condition. The second alternate option available to us is constant wall temperature boundary condition. So when you give constant wall heat flux boundary condition, for example, if you see the sectional view, this is the circular tube. Inside you have the fluid, and outside you are giving constant heat flux on the outer cell of the tube. So here, if we measure the temperature of the fluid at a different points from the inlet, let's say we measure at inlet and somewhere here at a different locations along the flow direction for the fluid, and we will measure the temperature of the wall, that is solid temperature. So this is your fluid temperature and this is the solid temperature. So basically this plot presents the axial variation of bulk fluid temperature, that is temperature of the fluid, and the wall temperature. So here you can see the bulk fluid temperature is linearly varying between the value at the inlet and the value at the outlet. However, the wall temperature linearly varies in the fully developed region only. In the developing region, it is not linearly varying. You can see the nature of variation for the wall temperature. So, this plot gives an idea that if it selects two axial locations, let's say I take 2 points, let's say this point is A and this point is B. So what is the value of temperature at point A? Wall temperature. This is the value of wall temperature at point A. And how much is the wall temperature at point B? This is the value of wall temperature at point B. Let's say I write as TA and this I write as TB. So from here we can say that this TB is greater than TA. That means temperature at point B is greater than temperature at point A. So in this scenario, what will happen? There will be transfer of heat from point B to point A, because you see here in heat transfer we have studied that when you consider a solid material, if you maintain the two ends at a different temperature, let's say left hand is A, right hand is B, temperature left hand is TA, temperature right hand is TB, and TA is greater than TB. In such scenario, there will be heat transfer by conduction from the point at high temperature to a point at low temperature. So because of which you can see here in this circular tube inside the solid wall. So this is the sectional view, you can see this is the thickness of the solid wall. There will be heat transfer in the actual direction from the point at B to the point at A. So if I make a 3D diagram, this is how a tube will look like. And there will be transfer from this point to this point. So you can see here in this diagram, this is the direction of fluid flow. However, this is the direction of heat transfer by conduction. So this is fluid flow direction. This is heat conduction direction. However, in case of a constant wall temperature boundary condition, the temperature at both the points are same. That's why there will be no scope for heat transfer in the axial direction. But in constant wall heat flux condition, there will be scope for axial wall conduction. So this is called your axial wall conduction, also known as the axial back conduction. Why the word back is used? Because it is acting in a direction opposite to the direction of the fluid flow. So that is, fluid flow is going in the forward direction and the conduction is occurring in the backward direction. So if you now closely observe, by considering the system, the sectional view of a circular tube, then you can observe that in textbooks they represent this as a circular tube, where the thickness is not represented. But if you take a sectional view of any actual circular pipe, you will see there will be some definite wall thickness. So zero wall thickness is practically not possible. So there should be some thickness for the circular tube. Whatever may be the small size of this tube does not matter. The thickness, there should be some definite thickness should be there. If we zoom into this thickness here, then this will look like this one here. You see, this is your solid domain, and inside the pipe you have the fluid domain. And when you apply this heat flux, we are applying on the outer surface. You can see here we are applying on the outer surface, and this heat will come by means of conduction to the inner surface, and at the inner surface there will be convection to the fluid. So we are applying some value on the outer surface. However, another value may be experienced. It may be same value or it may be different value depending on the situation. And that's why we represent this flux on the outer surface to be the flux applied, and the flux at the inner surface to be inner surface as the flux experience. So what is the role of this flux applied and flowed experience? If you consider the definition of this Nusselt number, then we will find out that Nusselt number mathematically can be written as HDH by KF. So here in this case, we can see here, we need the value of heat transfer coefficient H. So which can be represented as flux divided by TW minus TF. So in this case, you can see what is this flux. This is the flux at interface. Please remember, this is the flux at interface, which is nothing but the flux experience. That means the flux actually it is occurring. That means if you measure how much flux we are getting, it is not the actual flux we are applying. Flux applied and flux experience may be different or may be same, depending on the situation. And the wall temperature to be considered at the interface. This is your fluid, this is the solid. Wall temperature to be at interface, not on the outer surface of the tube. And the fluid temperature to be the bulk fluid temperature. That is average of the temperature at the sectional view of the fluid here. So you can see here, here I have explained the concept, and this slide will give you an idea how thick or thin the wall of a circular or maybe a non-circular tube or a duct is. You can see here. Here you can see this is the thickness of the tube. Here you can see this is the thickness of the tube. And here you can see this is the thickness of this non-circular duct. Here also you have some thickness. So whether it is a bigger diameter or smaller diameter does not matter. Even you can see here also. You can see the wall thickness for this small tube is higher compared to this bigger tube. For example, you see, suppose we are taking a circular pipe of radius, let's say 1 centimeter, and thickness may be 1 millimeter. Okay, let's say 10% of the radius. So let's say thickness is 10% of the radius. So R by 10. If you reduce the radius from 1 centimeter to, let's say, 10 mm, in that case, if you apply this concept, then this thickness should be 10 by 10, 1 mm. Okay. But practically having a pipe or tube of 1 mm thickness may not be possible. Or let's say if we make it to, let's say, 2 mm, in that case, here we need to have a 0.2 mm thickness. So from manufacturing point of view, 0.2 mm thickness may not be possible. Secondly, if it is possible also, then also it may not sustain the pressure created by the fluid flow. That's why there should be a definite thickness of the ducting system, and the thickness cannot be reduced beyond a certain physical value. So in such case, what happens? The relative thickness. What is relative thickness? The thickness of this tube compared to this radius will be higher as we gradually go on decreasing the diameter of this tube. So to understand to this, you can see here, this is the actual photograph of the sectional view of microtubes. So you can see here, you see a microtube having diameter 920 micrometer. So this diameter is 920 micrometer, that is 0.92 millimeter. And here you can see this is the thickness. And when now the diameter is reduced from 920 micrometer to 86 micrometer, you see here the thickness of this tube is approximately same or even greater than the diameter of the tube. So that means for a microtube, the relative wall thickness will be higher compared to the inner radius of the tube or the ducting system. So this is how I have represented relative thickness, that is radius to the thickness will be very high in case of a very small in case of a microtube, because thickness will be high, whereas in case of a conventional tube, the radius to thickness will be very high. So we get ample scope for heat conduction. So to explain the heat conduction again in detail, you see here in the sectional view of a in the transverse view of this circular tube, you can see we are applying wall heat flux on the outer surface of the tube. Ideally, what should happen on the sectional view, when you are applying this wall heat flux, they should radially come from the outer surface to the inner surface. They should come radially. Okay, so this way it will go to the inner surface, and at the inner surface there will be heat transfer by convection. So the fluid flowing in the tube that carries out the heat that reaches from the outer surface to the inner surface. This is the normal concept. However, what is happening as we discuss here, because there is a difference in temperature at these 2 points here and here in this diagram we have seen we have higher temperature towards the outlet compared to the inlet. Since temperature here is more compared to this point, there will be heat transfer in solid. There will be heat transfer in solid in this direction. So you can see, and this will occur by means of conduction. Whereas fluid is flowing in this direction, which is the direction for the convection. So since conduction is in a direction opposite to the convection, that's why this is called axial back conduction. That is conduction in the axial direction in the backward direction. And if you consider a non-circular tube, then this will be the axial back conduction inside the solid medium, and here there will be the heat transfer by convection by the fluid in the forward direction. So what is the importance of axial back conduction? What is happening here? Whatever the heat we applied, ideally move from here to here, and from here it should go to the fluid. But because of this axial conduction, the heat will move maybe something like this. That means instead of going here, it will go here, because two components are acting. One component is in this direction, another component is in this direction. Together you will have a resultant component, something going in this direction. So that means heat reaches from this point to this point, and from here it gets convected. That's why if you are applying constant heat flux on the outer surface, here at the interface we may not get constant heat flux. Here heat flux may be high, here heat flux may be low, because of which the thermal performance or the heat transfer coefficient value will be distorted, because of which the overall thermal performance will also be affected. So, madam, how much time I am having? At what time I have to stop? Please just let me know, so that accordingly I will schedule go on talking. Are you getting my voice? Madam, are you getting my voice? Hello.
Yes, sir. Actually, it's scheduled scheduled to 12:45.
Okay, so I have to stop at 12:45. No problem. Okay.
Yes, sir.
Okay, thank you. So now we will talk about heat transfer and fluid flow in mini channels. And what will be the fluid? The fluid will be single phase. If you are considering liquid, means it will remain in liquid phase only. If you are considering gas, means it will remain in gas phase only. And what we are considering here, we are considering a mini channel. So what is there? We have a conventional channel, then you have a mini channel, then you have a micro channel. That means conventional channel hydraulic diameter is greater than 3 millimeter. Already we have discussed. This is 3 millimeter to 0.2 millimeter, and this is less than 0.2 millimeter. So when mini channel means diameter, hydraulic diameter is more than 0.2 millimeter, but greater than less than 3 millimeter, but greater than 0.2 millimeter or 200 micrometer. This is the schematic arrangement for a mini or micro channel based heat exchanger test section. So this basically represents the actual photograph that I had shown you earlier. You have the test section here. That means your micro channel or mini channel will be present here. Fluid enters into the system here and leaves the system here. We are measuring the fluid temperature at the inlet and the temperature at the outlet, because practically you cannot measure temperature inside the fluid. So we are measuring at the inlet and outlet only with the help of thermocouples. And we are measuring the temperature of the wall or the solid at different points using the thermocouples as per our requirement. In the actual photograph, I have shown you how the thermocouple slots created to show the temperature values. So fluid enters into the system using a micro pump, and you can measure the flow rate using a flow meter. Then we can take the reading for temperature measurement and pressure measurement. So you want how much pressure drop occurs, we will use a differential pressure transducer, and both will be connected to a computer along with a data acquisition system. so that we can continuously monitor the values, and we can record it as per our required frequency. Let's say we want every second we want 2 readings, or every 2 seconds we want 1 reading. We can set the value and we can record it, and we observe how with time they are varying. Then you have the condenser and constant temperature bath and control valve to control the flow rate. I have already explained this one. And in the test section, here we have a mini channel. You can see this is called your mini channel array. What is array? More than one channel is called mini channel array. You can see here, this is one header and this is another header. Header means nothing but a small volume where fluid can be stored here. And this is the inlet from the bottom, and this is outlet from the bottom. And from the inlet header to outlet header, fluid is flowing through this channel. So you see here, this is channel number 1, channel 2, channel 3, channel 4, 5. This way there are 15 number of channels are there. And this channel, if you see sectional view, these are the dimensions here. It is 1.1 millimeter width, and inter-channel spacing, this inter-channel spacing is 2 millimeter, and the depth of this channel is 0.772 millimeter, and the hydraulic diameter comes out to be approximately 0.9 millimeter. So 0.9 millimeter is between 3 and 0.2 millimeter. So this is called to be a mini channel. And this shows the transverse sectional view here in the arrangement. You have, this is your mini channel system. Fluid enters from the bottom here and flows along this parallel channels and again moves in the downward direction. At the bottom you have a heater to heat the system so that fluid gets heated here in this case. And at the top you have a transparent glass used as a top cover so that we can see the flow, and we can try to do the flow visualization in case of a two-phase flow systems. Always doing experiment may not be possible because experiment requires lot of effort and lot of money also to purchase this hardware equipment. So the alternative is to simulate them using a computational fluid dynamics with the help of softwares, or even we can write our own program also to simulate. So basically what is simulation? This is called numerical modeling. That means prediction of any of the desired parameter, maybe temperature or pressure drop or flow pattern, everything here. So now here we can have a very simple question in our mind. We have channel number 1 up to channel number 15. Fluid comes to this reservoir here and leaves from the reservoir here. So now does flow rate in every channel is same or they are different? This is a question comes to our mind. Experimentally, this cannot be verified because you cannot measure flow rate here. However, this can be verified through numerical modeling. Secondly, what is the boundary condition at the solid fluid interface? We are giving constant heat flux at the bottom of the substrate. However, what is the heat flux experienced at the solid fluid interface? That also cannot be measured experimentally, which can be simulated or predicted numerically. So you can see here, considering there is a symmetry about the center line, we can have a numerical modeling of the 50% part. This left hand portion is here. So this is your inlet way and this is the outlet way. This is your inlet header. This is the outlet header. And here you have the 8 number of channels. 1, 2, 3, 4, 5, 6, 7 and 8. And 8th one is partly it is there, so it is a 7.5 channels only. Now we can simulate and evaluate how much is the flow rate in every channel, and we can plot it here. You can see here in every channel, whatever the flow rate you get in the 8th one, which is 50%, we can double it here and you can find out. Now theoretically you can calculate how much should be the ideal flow rate. That means let's say 150 ml is coming per minute. And there are 15 channels. So 150 ml by 15. So it should be 10 ml per minute in each channel. And from simulation, you can calculate how much is coming. So This is the average value, this is straight line, and this stars given here is the actual value of flow rate for a Reynolds number of 867. That means you can see here, gradually the flow rate is decreasing as we shift from the central channel towards the array. Because you see here, central channel will have maximum flow rate and the extreme last channel will have the lowest flow rate. The reason is that you can see here, this is the inlet and this is the outlet. Always fluid will try to pass through the shortcut path. So you can see here, this will be the shortest path. However, this is the longest path. So fluid will never try to go through a longest path. That's why flow rate in this last channel will be the lowest here. Our flow rate at the central channel will be the maximum value. So you can see here the flow rate corresponding to the central channel, maybe the fifth channel, like this. Then we can also simulate this axial back conduction and we understand it. So I only explained the concept. Now we need to understand what is the impact of this axial back conduction. To understand this, we can do the simulation. You see here, the overall procedure of simulation I am not going to explain here because time is limited. It is not possible to explain how to do the simulation in a 1.5 hour class or a talk. But I will just tell you what are the outcome so that we can understand the concept. So here we are considering, let's say we will take one plate here. Let's say this much thickness plate we will take. And in this plate, we will engrave one channel. That means we need to remove this much material here. We need to remove this much material so that we get a channel here or something like. So this is what we get it here. So this is called the substrate, solid substrate. And in the front view or sectional view, we will be able to see this one here. What we are doing, we are giving constant heat flux at the bottom of this plate. Here we are giving constant heat flux. And we are insulating this left hand face and we insulating the right hand face. Also, we will at the top, we will have a cover plate which will act as an insulation as well as it will cover the open channel. It will form a closed channel. And in the simulation, we have not considered this plate. Directly, we have implemented insulated boundary condition at the top, insulated at the extreme left, and insulated at the extreme right. And if you take the transverse section, then you see here, this is the wall thickness, this one here, and this is the fluid height, channel height, this one is the fluid height. Considering symmetry, we need to simulate either the left portion only or right portion only. So let's say I decided for the right portion, or you can decide to take the left portion only as you like. So whenever we are taking the a part, then we will have a symmetric boundary condition along the plane of symmetry. So here we will solve this problem with some basic assumptions that we are solving under steady state condition. We are solving for a laminar flow, that is flow rate is very small. The fluid is incompressible in nature. So the common fluid is your water is the best fluid to consider to be incompressible. We know that the thermophysical property, let's say density, viscosity, etc., changes slightly by changing the temperature. However, since temperature change is small, so the thermophysical property change is very small. That's why you assume them to be constant. And any heat loss from the system by radiation or natural convection is neglected because in practical situations we will be insulating the outer surfaces. So when you carry out the three-dimensional simulation, these are the details that I'm not going to discuss it here because this is the beyond the scope of this today's 1.5 hour talk. So what we will be doing here, we will be studying how the performance gets affected if you change this thickness. If you change this thickness, that means overall thickness of the plate. So somebody takes a thin plate and somebody takes a thick plate. So will in the both situations we will get same result or we will get the different results. So to define this thickness, we are representing this channel height as delta F, and this below the channel height we call as delta S. S for solid, F for fluid, delta is for the thickness. We are changing the flow rate of water, and we are also changing the material. Whether we will take aluminum, we will take copper, we will take steel. Are they behave exactly same or there is a change? So for water, Prandtl number is fixed. These are the thickness of the substrate we are taking. These are the different materials we are taking, and this is for the Reynolds number. What is KSF? It is Ks by Kf. Ks is the thermal conductivity of the fluid. Ks is the thermal conductivity of the solid, and Kf is the thermal conductivity of the fluid. So here fluid is constant, that is water. Only solid is changing. So from aluminum, steel, copper, accordingly the Ks is changing and thickness is changing here. Then to understand this role of axial wall conduction, we are introducing a parameter called dimensionless flux. What is dimensionless flux? How much flux we are giving some flux here, and we will experience some flux here. So theoretically some flux we will experience, practically some flux we will experience. So this is your the actual flux experience divided by the ideal flux should be experienced. That is actual flux value divided by the theoretical flux value, that gives the dimensionless valid flux. So if phi is equals to 1 means there is no axial wall conduction or axial back conduction. If phi is more means there is axial wall conduction or axial back conduction. So to understand this one, let me take to the next plot here. You see in the sectional view, we are giving the flux here at the bottom. Okay, so what happened? This heat will come to this place here. This heat will maybe go like this here. This heat will go here. This heat will go somewhere here. Okay, so this way the heat will move inside the solid, and it comes to the interface of the fluid. And from the interface of the fluid, it is going into the fluid by means of convection. So here what we are doing is, let's say we give here 10 watt per meter square. We need to know how much heat will reach here. So if we consider it is uniform everywhere, then how much heat should go here? 10 watt per meter square multiplied by this area. This area is this length and the third length direction here. Let's say this is L1 and this length is L2. So it is 10 multiplied by L1 multiplied by L2. That is the total heat given here. And here let's say this is the flux value. That is Q dash Z multiplied by this length. So let's say this is your delta F is the height and omega F is the width. So it will be 2 delta F plus omega. So it is 2 delta F plus omega. This is the perimeter of the interface multiplied by the length L2 multiplied by the flux here Q dash Z. That is equals to this value. So from this relation we can calculate this one here. How much is the ideal value? Then actual value divided by ideal value gives the flux here. You can see in this plot. Let me zoom this 4 extreme plots here. This indicates the length along the axial direction, that is along the length of this substrate. So x is equals to 0, 2x is equals to L. Represented this is we are representing Z. So Z is equals to 0 inlet, Z is equal to L is outlet. Then the Z star is represented as Z by RE PRDA. That is we are writing in the dimensionless form. We are dividing by Prandtl number, hydraulic diameter and Reynolds number. Okay. So you can see in this case everywhere the phi is same and this is equals to 1. That is the actual flux at the interface is almost same as the ideal flux. That means there is no axial back conduction present here in this problem. However, in this case, you can see here, for one case, which is for delta SF is equals to 1, that is thickness is very small, almost throughout the length, the value is equals to 1, only it is a slightly more near the inlet. But let's say for delta SF 24, you can see the plot here, and this is the variation. Nowhere the value is 1 except at one point only. Since flux reduced here, so flux is increased here, so that there will be energy balance. If you correlate this with the channel inlet with the channel outlet, this is the inlet and outlet. If you remember, we told that here you have a higher temperature and here lower temperature. Because of higher temperature here, there is heat transfer by conduction in this direction. So what will happen? Here the flux value will come down. So you see here, flux is decreasing from the ideal value of 1. So it comes from 1 to the lower value here, something around 0.4, 0.55. And here, since it is added, so here it goes up here. So it is coming from 1 to maybe 1.2 or 1.3. That means axial conduction will distort the boundary condition at the solid fluid interface. And since the boundary condition at the solid fluid interface gets distorted, the thermal performance will also get distorted, because you see we are defining Nusselt number as HDH by KF, and H we are taking as flux at the interface divided by TW minus TF multiplied by DH by KF. So that means here the flux at the interface, the wall temperature and the fluid temperature, these three are very important. So if there is a change in this value, then Nusselt number will also change. And here in this plot, I talked about how the flux is changing along the length. Then in the next plot, you can see how the fluid temperature and the wall temperature is changing. You see here, this is the plot I had shown you earlier, which normally you find out in textbooks here. Linearly varying fluid temperature, and this is the wall temperature. But in this case, you can see fluid temperature is not linearly varying. This is becoming something like this. That means from the inlet to outlet, fluid temperature is becoming like this instead of this linear variation. And wall temperature is also becoming like this. So this plot is close to that case of a wall temperature, constant wall temperature boundary condition compared to a constant heat flux boundary condition. So because of this, if you compare the Nusselt number plots, you can see here, this is the Nusselt number corresponding to constant temperature, and this is the Nusselt number corresponding, constant flux and constant temperature for a rectangular tube or rectangular duct. And you can see here in this situation, Nusselt number is close to this value, that is remaining almost constant throughout the length. But in these situations, it is changing here. This is because of different conductivity values and different thickness values. So overall, we can conclude that the conductivity should be less, the flow rate should be high to avoid axial wall conduction in a microchannel based heat exchanger devices. So with this, I will conclude my talk here. I hope I tried my best to explain this concept in the simplest possible manner. Still, if you have any doubt, you can ask it. I will try to clarify the doubt now. Thank you all.
Thank you, sir.
Thank you very much, sir, for giving us more information on heat transfer and fluid flow on microscopic scale. Now we have 15 minutes for discussion. Delegates can now have questions.
Mhm. Unmute କରିବା ପାଇଁ
Hello, sir.
Hello.
Yes, sir. In that slide, axial back conduction, there in constant heat flux condition, that slope changes. That means it is not a straight line. The slope changes after some time. Why the change in slope is there?
Okay, let me go to the slide. Are you able to see the slide now? Are you able to see the slide now?
Yes, sir, it is visible.
Okay. So you are talking about this slide. You are talking about this one.
No, sir. That where you axial back conduction.
Okay, let me go to the back. This slide, huh?
Yes, sir. Yes, that. Yes, yes. In this slide, the graph.
This one, huh?
Yes, sir.
You see, this a plot I have taken from a standard heat transport textbook. You see, the concept is, let's say we take a circular tube, and inside the circular tube, let's say water is flowing. Water enters here and leaves here. We are giving, let's say, suppose total 10 watt we are giving, and surface area is coming out to be, let's say, 0.5 meter square. So 10 watt is applied on 0.5 meter square area. That means our flux is 20 watt per meter square. That means in every 1 meter square area we are giving 20 watt. So if that means every 1 mm square, let's say this is a 1 meter square area, we will, let's say, divide into small divisions. So that means suppose we are giving here total 20 watt, and I have divided into 4 into 4, 16 divisions. So 20 by 16. So this much is the heat enters into the on the outer surface through every this small area. That means if I take a slice of this tube in the axial direction, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I make 10 division, and total 20 watt, 10 watt we are adding. That means in the first 1 by 10th length, 1 watt will be added. Next 1 by 10th, another 1 watt will be added. So we can calculate how much is the temperature rise. The basic formula is Q is equals to m dot Cp delta T. So what is delta T? Fluid outlet temperature minus inlet temperature. So here for the partial length, for example, this is your inlet and this is the outlet and this is the first division. We want how much is the temperature of fluid here. So this will decide how much heat we are adding. So using this formula, see the delta T is T outlet here minus T inlet here. So outlet is means here. This one we will calculate as outlet. So from this relation, mass flow rate we know and Cp value we know, and from this relation how much heat is given, that will give you how much is temperature here. Accordingly, the temperatures if you calculate at different points, then we will see there will be a equal rise in temperature for equal length we travel along the flow direction, indicating that the temperature of the fluid between the inlet and outlet will vary linearly. That means if you are doing experiment, as I shown you in the one slide, we measure the temperature at the inlet and outlet only, but if we need the temperature somewhere in between, so what we have to do is, for measuring temperature somewhere in between, let's say we need temperature here or temperature here, we can measure at the inlet and outlet only. So we need to interpolate. How to interpolate? Let's say total is 3 meter, and here the temperature is, let's say, 20 degree, and here let's say temperature is 50 degree. That means in 3 meter there is a rise of 30 degree. For 1 meter there is a rise of 10 degree. So here it will be 20 plus 10, it will be 30, and here 30 plus 10 will be 40. If you have to plot the temperature here, then it will go like this. At the inlet it is 20, outlet is 50. After 10 meter, here it is 30, and after another 10 meter, here it will be 40. This is called linear variation of temperature. So you can predict the temperature at any location to be linearly vary. This is a theoretical concept, but practically the temperature here may not be 30. It may have gone something like this, not linearly vary. This is because of axial wall conduction. Is it clear now? Is your doubt clear now?
Yes, sir. Yes, sir. It's clear, sir. And another thing I want to ask, sir. You said about that numerical modeling and the stimulation, sir. I mean, which software you used for that? ANSYS or any other software?
Here we are using ANSYS Fluent. Actually, ANSYS is a brand name, and ANSYS has so many softwares. Out of so many software, there is one software called ANSYS Fluent. I have used ANSYS Fluent. Even some work we have also done without any software also, because you see, CFD is not mandatory to use any software. Even you can write your own code also. CFD is nothing, the software is nothing but a commercial code. That means somebody has written a code, they are selling it, you are paying the money, you are using it. So I have used ANSYS Fluent. Some few plots also I have that we have developed without any software also, that I can show you also. Are you able to see the screen now?
No, sir. Screen is not visible.
Okay, let me share it. Are you getting the screen
Yes,
now?
yes, sir. Yes, sir. Now it is
Okay,
visible.
so these are the velocity contour diagrams. You see very complicated geometries. This we created using own code. That means I have written my own programming using Fortran language, and what are the results I got, that I used another software to create the contour plot. So there is a software called TechPlot. Is there? TECPLOT. TechPlot helps to create contour plot. It will not give a solution. So these are from that own programming with contour plots. But I have some other plots. For example, you see this one. These diagrams created in the solved in the ANSYS Fluent.
Okay, okay, sir.
Okay, thank you.
Sir, is there any source means where we can get the process in means in which way we have to stimulate, means how to set the parameters, and that discretization model, which model to set for better accuracy? Means,
Okay, you see, for that one, you see, for doing simulation, first you have to understand the CFD. That means your fundamentals of CFD you have to learn. You should know the background theory. Then only you will be able to know. For example, you see in one slide I have written here. I will let you go there. Few things was written. For example, you see here in this slide, 3D numerical heat transfer done on commercial CFD platform. Pressure discretization using standard scheme. So there is a one scheme called standard. If you are using a software, in the software there will be a drop down menu will come. In that drop down menu, 2-3 options will be given. You have to select one option. Now question arises, how to know which option is the correct one?
Yes, sir.
Blindly you cannot select any random option. If you learn the CFD theory, then only you will understand what is the meaning of standard scheme, whether for this particular problem I should use the standard scheme or something else, by learning CFD only. So what you should do is, you should learn CFD first, fundamental theory. If it is being offered in your institute, you can learn it yourself. Otherwise, nowadays online so many resources are available. Even I can suggest you names of some books also. Personally, I have a YouTube channel. If you are interested, you can note down the link for this YouTube channel. There I have recorded videos for this subject CFD. Even on YouTube, you will find out CFD recorded videos by some reputed professors also. I guess tomorrow morning, Professor Suman Ghosh is going to give a talk. His video is also available on YouTube on CFD. Here, the link for my channel is youtube.com/user/mkmoharana, MKMOHRANA. Here, if you go down, you will find out you have a section called computational fluid dynamics. Here, I have tried to explain things in a simplest manner. Here, for example, you see here in this, you can see this is a problem on two-dimensional heat conduction in a cylinder. The basic theory have been explained, and whatever the outcome temperature values, that I converted into contour diagram with the help of third-party software. As I told you, there is a software called TechPlot. So no commercial software used here for to create this diagram. So I will recommend to refer to videos available on YouTube. And regarding books, on the first lecture of my YouTube, I have given name of so many books. There you can see the list. But immediately I can suggest one book. There is a book by Professor P.S. Ghosh Dastidar. This is a very simple book. This one, Computational Fluid Dynamics and Heat Transfer by Professor P.S. Ghosh Dastidar. This is a book, very small book, nicely written, easier to understand. So I will recommend first start learning from this book, then slowly you can refer to some higher CFD books, like this is another book, An Introduction to Computational Fluid Dynamics by Bistag and Malala Shekhar. And then this is also another very interesting book by Professor Atul Sharma from IIT Bombay. However, I will recommend start learning CFD from this book.
Okay, sir. Thanks.
Okay, thank you.
Yes, sir. You means you explained very nicely, but that stimulation part very shortly means due to the time constraints. Okay, sir.
Obviously, you see, actually here I am teaching to student this subject CFD. We are taking around 13 into 3, 39 hours, minimum 39 hours we are teaching. So within 1 hour, it is impossible to teach anything. So that's why you see here. For example, here also I have slides for on the fundamentals of CFD. You can see here I have 101 slides. So this is only for the introduction class only. So difficult to describe everything here in a single class of 1.5 hours only. Okay. So in future, if you have any doubt, you are feel free to contact me. I will try my best to help you in getting learning materials and resources. You can note down my communication mail ID also. I think yes, so you can note down here. My personal mail ID is mkmoharan, moharan@gmail.com. You can write an email to me. I will try to answer you. Also, if you want to talk with me, my office mobile landline number is also given here. 0661-246-2533. You can dial during office hours. Thank you.
Thank you, sir.
So it was my pleasure in giving a talk to the persons now present online, and I thank the organizers once again. Is there any question, or I will stop sharing the screen now here?
Okay, sir. Thank you so much. So now we have come to the end of today's program. I hope you have enjoyed this day and gathered some new and innovative information in the field of transport phenomena from our esteemed speaker. I must thank you all for your kind and cooperation, and I look forward to meeting you all here tomorrow. Thank you.